I think that some of you know me. I think this is my second class. So I don't need to go into full-scale introduction. But basically today is unsupervised learning. I find it very interesting and I like it because I think that this is one of the future, or this is the future of machine learning, right? The problems that we have with machine learning is now everything has to be labeled. You have to have labeled data, it has to be perfect, data has to be good. And I think that future solutions in getting around this problem where the data has to be pitch perfect is, trying to go unsupervised learning or trying to combine unsupervised learning with supervised learning in a way right now that we call semi-supervised learning, which is gaining a lot of traction in the field. But to understand the connection between supervised and unsupervised learning into, or the combination of it into semi-supervised, I think we have to understand unsupervised. And so I'm just going to assume that, your supervised learning class, you remember everything. And yeah, we're gonna go. Make this full screen. Okay, good. Okay. So today we're just going to talk about unsupervised learning. We're going to talk about K-means, which is the, I would say, the entry point into unsupervised learning. It's the default algorithm. What is good about K-means is even as simple as it is, it's still predominantly used a lot to solve problems. I mean, even in high complexity systems, you still see K-means popping up all the time. And after that, we're going to talk about something that is a personal favorite of mine because it made me want to win a competition during my master's after I used it for feature extraction, principal component analysis, and I think that this will give you the base for extra research. And if you want to do extra research on your own, you can start to look at different clustering methods. You can another personal favorite of mine is spectral clustering, which you can check out in your spare time. But I think that understanding K-means and understanding principal component analysis will give you the base for whatever new algorithm that you want to check out on your own. So supervised learning, I mean, I'm sure we remember this from our supervised learning class. You have training data, you have a machine learning algorithm, and your machine learning algorithm is supposed to use your training data, which is labeled. That's why you have X, Y. The data point is X, the label is Y. You pass that into a hypothesis function. Your hypothesis function is supposed to learn a new prediction, Y hat. That's Y with the cap, right? So you're supposed to learn this new prediction or this new ability to predict this by minimizing a loss function between your label data and what your hypothesis function is giving you. In a sense, what you're trying to do in simple English is that you're saying that, can I learn a model that can try as much as possible to look at my training data and give me and predict the labels? And if it can predict the labels on my training data, then I can assume that when I give it new test data, that the labels that it predicts are correct or close to being correct. And that is why we say minimize the loss, because we can, I think a much more mathematical term will be it tends to be incorrect, just like we say it tends to zero, it tends to infinity. So yeah, I mean, that is basically supervised learning. I'm sure we learned a lot of methods. The complexity of supervised learning, which I was talking about, is that you have to have all your data, labeled. So if you have 5,000 data points or 10,000 data points, you have to have the data points and the label. So you have to go, let's say you want to learn to differentiate between a dog and a horse. You have to take pictures of dogs and pictures of horses, and you have to manually say, this is a dog and this is a horse on each picture, right? And that's a problem because it's now very labor intensive and work intensive, and we're trying to minimize the work. And so we're saying, hey, can we have another set of algorithms that you don't need label data. Now, one of the things I would say now, and maybe some people will dispute that with me, but unsupervised learning is not as advanced as supervised learning in both. And so a lot of things that we do now is still very supervised, but understanding this unsupervised world will help us get through. And maybe you would even design the next breakthrough unsupervised learning algorithm, right? So unsupervised, what are we doing? We don't have label data, right? And so we have an hypothesis function and we have a prediction. Now, what are they doing, right? In this case, what is your hypothesis function? Learning, right? Your hypothesis function, in a sense, is learning to make connections, right? As learning to make connections between the training data. So it's saying this picture of a dog looks similar to that picture. I might not know it's a dog. I might not be able to say it's a dog. But then if I see a new picture, I know where it should go. Should it go into the ones that have clustered together as dogs, or should it go into the ones that have clustered together as horses? And so what you're trying to do is that you're trying to make connections between this existing data, and you're trying to extract the existing classes, in a sense, clusters, right? And you hear this word a lot from now, clusters, right? You're trying to extract these existing clusters. Some mathematicians would just try to, I think you see that in the slides later, they might try to complexify things and say, hey, your hypothesis function is learning a mapping from X in n-dimensional space to X in n-dimensional space. And your prediction is supposed to map new X in n-dimensional space to an X in n-dimensional space. So now that is very complex. But what it means is, for instance, it might mean that, let's say you have all the pictures of a dog, and you're able to learn a centroid, which is basically the k-means, or you're able to learn a central parameter of what dogs are, or what they have in common, or what those pictures have in common, and what horses have in common. And so in when you're doing prediction, what you're trying to do is you're maybe trying to map your new picture, which is a dog, to an existing picture that existed in your data set, right? And trying to classify it as maybe being as close to that picture, which is maybe a dog, or close to another picture, which is a horse. So in a sense, you can say it's mapping one data point to another data point. So don't let mathematicians confuse you if you hear that in the future. Yeah, so what are the three elements of supervised learning? We have an hypothesis function, as always. We have a loss function, as always. And we have to define how to optimize our loss function. I'm sure you've heard this a lot. Hypothesis function, loss function, optimize loss function, right? But what do these mean? What are we trying to do? What if we say we have an hypothesis function, what is it, right? And what is your loss function, in a sense, when it comes to unsupervised learning? And supervised learning is pretty straightforward, but unsupervised, it's easier to conceptualize unsupervised learning in your head than to look at the maths. And I always think that it's the reverse for supervised, where when I say the maths is simpler, but conceptualization is a bit harder. But with unsupervised learning, the mathematical conceptualization, I think, is harder. But that's what we're going to do. So unsupervised learning, you have an input data sets, no labels. And if you have questions, you can just stop me and I'll try to answer your questions. Yeah. So input features, you have X. You can have X's from n real dimensional space. How many of us now know how to read all this mathematical notation? I mean, you can just put it in the chat. Comfortable, not comfortable, struggling, I totally hate it. I mean, let's take a poll. You Are you comfortable with this mathematics, with mathematical notation? Anybody? Chat? Struggling. Yeah. 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 A lot of at the beginning, it's at the beginning it's hard, I would say, but as you go more at it, it becomes simpler to the point where it's actually easier to write this in English. So yeah, X is from n real dimensional space. There are n samples of of X. So that is the number of learning points you have in your data set. And it's n real dimensional space. So it might have different features, right? It might have n dimensional features. So you essentially have a row of n columns. That's what it's saying. That's what your features are. In an image, what will that correspond to? It might correspond to, if you have 256 by 256 by 3, which is which is 3 channels, red, blue, and green. It might correspond to 256 times 256 times 3. That will be your n, and the number of images will be your m. Now, model parameters, right? You are going to learn a model that draws its parameters from a k real dimensional space. Um, what k is, it now depends on the model or whatever you're learning. And then you have an hypothesis function. Now, this is what I was trying to explain earlier to you, that maps n real dimensional space to n real dimensional space, right? So if we remember correctly, in supervised learning, you were mapping n real dimensional space from the data or from the input features to whatever dimensional space your target is in. But in your hypothesis function for your unsupervised learning, you're learning n real dimensional space, n real dimensional space. And like I explained, when you think about it in terms of clustering, it makes sense, right? Um, yeah. And then we have a loss function. Loss function is going to take what you have and what you're supposed to have, and then it gives you a number, right? Measures the difference between a hypothesis and actual inputs, right? And I know that that might be a bit confusing. So when you think about it in terms of clustering, right, you might say this. So let's think about dogs and horses, which is what we started with, right? What the loss function is actually saying is, if you have a new picture of a horse, right, your loss function should be able to determine that the distance between the picture of your horse to existing pictures of the horse within your data set is minimal. And therefore, it's supposed to say, hey, this looks more like a horse than a dog. And so your loss function should be able to say, I need to classify this as a horse. So you minimize that distance by making sure that it is classified as a horse and not classified as a dog. And that is what this loss function is. And yeah, and we come back to the end game machine learning optimization, which is you minimize over your parameter set, minimize over theta, giving a summation of the losses on all the data points, given the difference, the losses on the hypothesis and the input features on all of the data sets. So this is what this simple math uh, this and this is our end goal. This is exactly what we want to try to do. And that is one of the things about this mathematical notations, is that we've been able to simplify this problem into just one simple line of, you know, what we need to do. Okay, now let's talk about hypotheses and loss functions, right? Yeah, like I said, the framework is odd. It looks odd. Well, what does it mean to have an hypothesis function approximates the input, you know? And in a sense, yeah, this is one question that, you know, I saw here, and someone has asked me this before, like, if you're talking about this mathematics like this, right? You know, if you're saying that this is a hypothesis function, it maps n real dimensional space to n real dimensional space, isn't the best hypothesis function just a function that maps a value to itself, right? I mean, and yeah, in a case where, you know, your k, in a sense, your parameter set is equal to m, yeah, that will be in a case where you have k classes, right? Let's say you have 30 images, right? and you say, I want 30 different clusters, or I want 30 different classes, right? Everybody will be classified as their own. If we think about people in the school and we say, how many are we? And we say, we want to do a breakout room. We want to do a breakout room, and we put exactly the number of people on the call. What happens is everybody on the call is going to end up in the breakout room alone. I mean, I hope we know what breakout rooms are uh, on Zoom. But it's usually not like that. What happens in reality is that you have a constraint. You have a constraint on the number of breakout rooms that we need to create for people to interact. So let's say, for instance, we need to create 3 breakout rooms. Then our hypothesis function is then limited. It's limited in a sense that it cannot just map each person to their breakout room. It has to find characteristics by which to put 2 or 3 people in breakout rooms, depending on what your restriction in terms of the number of classes are. And so, yeah, this can be the optimal case, when you have m is equal to k, but it never is like that. And I mean, even if somebody gave me a problem like that, I would say this is possibly a problem that is not well defined. So now that we say that there's a restriction in the hypothesis functions because there's a restriction in the number of classes, and so you cannot just map x to x, we're now going to go and talk about 2 algorithms that are interesting. K-means. Now, K-means is very simple, intuitive, and interesting to understand what is K-means. So K-means is something that you can easily visualize. So let's say um, let's say we wanted to break this out into 2 breakout rooms, right? And we wanted to learn a hypothesis function that can break us into 2 different rooms based on some characteristics or not. I was recently on a Zoom call where the person on the Zoom call made 2 breakout rooms, and somehow the Zoom algorithm puts all men in one breakout room and all women in another breakout room. It was pretty fascinating because I was fascinated as to, what the programming could be like. I'm sure it's essentially random, but in a sense, I'm one of the things I know mathematically I'm fascinated by is the structure of randomness, right? And I was fascinated by that. But let's say we have a hypothesis function that is meant to, based on certain features, based on certain things, right? Based on certain features. Thanks for the comments. Based on certain features, you say, okay, fine. Um, I want to learn a hypothesis function that would do something else, right? Let's say that there's a constraint that there are certain people that they cannot be in the same breakout room because they are fire. It's like fire um and petrol. It's just gonna burn. Nothing is gonna happen, right? And you're saying, okay, fine. I want to. So let me explain what a breakout room is. I think we might try that. So I don't know if Teju can do that. Teju, I don't know. Can you do like
Yes,
breakout room
yes, I can.
for
Let me do that. Let me
Yeah.
randomly assign people to breakout room.
yeah, just 2, maybe just 2 breakout rooms.
Okay.
Breakout rooms.
Okay.
Should I? Are we to answer that?
And you can do that for like maybe 30 seconds or something, or one, and then we can come back so that everyone knows what a breakout room is.
Okay, about to do that. Is everyone in their breakout room? Yeah. Well, welcome back, everyone.
Yeah. How was our breakout room experience?
It was lovely.
Great. I'm glad you enjoyed it. Can you still see my screen? Anyways, can you still see what I'm sharing? Or do I
No,
have to share again?
No, we can't see.
Okay, I have to share again. That means. So yeah, so that's a quick experiment, right? To tell us what a breakout room is, and in a sense, it's just so the algorithm had to split us into. I think Teddy did 2 rooms, and then we had to split us into 2 different rooms, and it had to find. I'm sure he did it randomly, right?
Yes, I did it randomly.
Yeah, I'm sure that the Zoom algorithm did randomly, just hey, random people in different rooms. But what if we wanted to learn a hypothesis function that had certain constraints? 2 people here are fighting, they can't be in the same room. I remember when I was defending my PhD, and we had to invite like professors, and I was like, oh, I want this professor, I want to defend in front of this professor. And my supervisor at some point said, oh, no, you can't defend in front of these 2 supervisors, these 2 examiners, because they are fire together. I mean, when they're together, if one person is saying yes, the other person is saying no. They essentially hate to agree on anything. And so you don't want to be caught in the middle. So let's say there are constraints like that, right? Let's say there are constraints, there are other constraints. So how can we learn a hypothesis function that can separate, do this and do a breakout room in a sense, and put people in 2 different rooms, given characteristics, not just randomly anymore, but given certain features like put all the dogs in one room, put all the horses in one room, put all the people that let's say you have an hypothesis function that you have breakout rooms where they speak different languages, put people that speak different languages, that speak the same language in one breakout room, and people who speak another language in another breakout room. So these are all constraints, and these are all based on features, right? And so k-means is a way to say, now I want k centers. I want K classes, I want K points. And I want you, my hypothesis function, to create a model that can separate this into 2 classes, 3 classes, 4 classes, K classes. And in a sense, I would refer to it as K centers here, all right? And now this starts to make sense when you think about the hypothesis function mapping X to X, because here you have these points exist in a space. And now I'm going to talk much more geometrically. These points exist in a space, right? In n-dimensional space, and this exists in an n-dimensional space, right? And your algorithm is creating a separation between these 2 different classes in n-dimensional space. So if you have a new point, what it's going to do is going to say, hey, this new image, what point does it map to in n-dimensional space? And of course, it has to map to a point in n-dimensional space. And that is why our hypothesis function is, mapping x in x, a point, x in n-dimensional space to x in n-dimensional space, because we're mapping to a point in n-dimensional space. I hope I didn't confuse anybody by that analogy. Okay, so how do we do this? Yeah, let's go back to the maths. So how do we do k-means, right? How do we do k-means? One of the things you have to do in k-means, you have to say, what are the choice of the centers? So how many classes do I want? First of all, that's k. Let's say I want k of 2. So where do these centers have to be, right? Because you have to identify centers in the space of the input. So how do I choose the centers? Of course, my hypothesis function is going to help me choose the centers. And my hypothesis function here, and that is what this maths jargon is saying, is that, hey, I'm going to choose these centers, and I'm going to say, hey, whatever point is assigned to the center closest to it. So I'm going to minimize the distance between a center, between a point and the center that it is assigned to. So in a sense, I'm going to minimize the distance between the center. If I have a horse, I want it to be assigned to the horse center. And if I have a dog, I want it to be assigned to the dog center. Yeah, and the loss function is the squared error between the input and the hypothesis. Now, what this means, in a sense, it's not like unsupervised learning where you have a target and then you say your loss is, the mean squared error, blah blah blah, between your target and the output of your hypothesis. No, this one is different. This is merely different. The output of your hypothesis function is the center. So what is the distance? So to see how well you're doing, to see your loss function, you're going to take every point in your data set, and then um, you're going to look at the distance, the square distance between that point and the center that is closest to it. And if you have a very high loss, it means that your centers are very badly defined, and therefore, now when you look at the loss, you will now optimize your center, which is reassign the centers in a way that the distance between X that is assigned to a center and the center is minimized as possible. And this now becomes our optimization point. Simple so far? So how do we do this in reality, right? K-means objective is non-convex. I think that we should have done non-convex or treated non-convex problems. In supervised learning or optimization. Do we know what non-convexity means? Do you need me to explain? I think I even talked about it in my last class a bit when I was drawing the diagrams for the optimization, the loss. I don't know, maybe it's not this class, but I think I talked about it. But if you do not know what convex is, you can put it in the chat. Else I would assume that everyone knows. So yeah, it's non-convex, which means that you have the possibility of local optima. It doesn't have a smooth gradient towards the minima. It means that, there are many points within, for the mathematicians, there are many points within your optimization function where the y dx is equal to 0. And what that means is, if you remember further maths from high school, where they tell you that if you have during optimization, the y dx is 0 only at a maxima, a minima, and a saddle point, right? Now, what non-convex means, okay, so yeah, I was in my class, I remember. So what non-convex means, in a sense, is that, so I think the last one I gave it, I tried to explain it using a bowl. So what it means is, non-convexity means that there is a unique point, only one point within your optimization function where every other point is greater than it, right? So every other point to the left and to the side of that point is greater than it. And there is only one of such points, right? So what that means in a sense is, think about a bowl where a calabash where there is one point, which is the one bottom point, which is when you pour water into the bowl, this is where it goes. So this is what we roughly refer to as convexity. And those kinds of problems are easy because why they're easy, for instance, like the bowl analogy is that you just have to find where the water went, right? And then you know that that's the bottom pot, right? But if you have much more complex structures where, let's say, you think about Nigerian roads where there are many potholes, right? When rain falls, there are many points that it can gather, right? It can gather in that pothole, this pothole. So there are many minimas in a sense, and you don't know which one is best, and you cannot straightforward go from one minima to another minima. In a sense, you have a possibility, if you use the water analogy, of water being stuck in any one of them, even if it's not the best. Although we always want the best. Now, these kinds of problems are difficult because it's non-convex, so you can't just mathematically pour water. I'm trying to make it as simple as possible. Forgive me. But when you have many of those clusters, when you have many of, let's say, potholes, in a sense, when you think about Nigerian roads, you don't know which one is the best minima. You don't know which one is the best. And so what we say is that all of these different all of these different, not saddle points, optimas, all of these different optimas, we call them local optimas. And so it's difficult when you get into one to come out of it and go to another. And so those kinds of problems are difficult, and we call it non-convex problems. And I can tell you that this explanation is enough to get you into Google or to which other company or to there, but to get you to work in this new research lab.
Did you just say that?
Yeah, there, yeah. So
Okay.
don't worry, it's enough to get you in. I think I've given this explanation before, and yeah, they were pretty happy. So, but I mean, understand the maths, and that was fine. So, yeah, and it doesn't have a closed form solution. Yeah, what that means is, in a sense, there's a possibility that you cannot mathematically optimize it, right? Because if you mathematically optimize it in the sense of just pouring water, you might end up in one of those different local minimas, and then you don't know which of the local minimas you're in, whether it's a global minima or local minima. And what we say about problems like this is that they do not have a closed form solution. And so, like I treated least squares the last time, which had a closed form solution, you know, it was easy because we could now, I remember I took us through the derivation where least squares became as simple as just, you know, just a mathematical formula. But for this one, it's not like that because it doesn't have a closed form solution. So we resort to approximation. And when we say approximation, we have to do iterations. And this algorithm I'll talk about now is what we call the Lloyd's algorithm, or K-means. If you get to an interview or you want to sound fancy, say you're using the Lloyd's algorithm. and then, yeah. So what do? We want to assign points to the nearest cluster. And then we will compute the cluster center as the mean of all the points assigned to it, right? So we have dogs, and the cluster center for dogs is the mean of all the features of dogs, and, you know, into one default, we take the mean. So we say, I'm sure we know what mean is. Mean is add it all together, divide by n, or m in this case, right? Yeah. So, and then how do we do this? How do we start? We first of all, I mean, a lot of you are asking the right question. It might be, how do we get the initial center, right? So simple. The initial center is, you're going to do it randomly. So you're going to pick random, just pick random center, and then you keep adding, you keep clustering data points to their closest center, and then you recompute the center. So you start from a random point. You say, okay, which one is, let's say we have two, right? You start from a random point, right? You assign people to those random points, right? You find the mean of all the features of those things, the people that you assign to the random points. And then that becomes the new center. And then you reassign based on the new center. And then you continue doing this until convergence. And what does it mean, convergence? Until your result at iteration k+1 is not different from your result at iteration k. Raise hand. All right, go for it. Someone's asked a question, I'm listening.
Okay. Yeah, sorry.
Yeah.
Thank you very much for that explanation. My question is, can we have like a circle illustration of this? Do you mean that initially the clusters, let's assume it assigns them randomly, and then we try to draw a circle around them, then we see overlaps, and then we are trying to now separate the circles of clusters, kind of thing?
Okay, so I'm going to go straight to this one so that you can see it, right? So these are the data points. These are the data points on the graph, right? And red is supposed to be part of one class, green is supposed to be part of one class, and blue is supposed to be part of another class. That's basically what we know, right? So we started with 3 random points. We just picked it randomly, anywhere in hyperspace, right? So we have these 3 black points, which is what we started with, right? We computed based on the distance between these points and the centers. We say, okay, which center is closest to each point, right? And when we assign that point to the center closest to it, right? In the next iteration, we create a new center. All right. So in this particular iteration, all of this was defined as red because if you look at it, the initial black dots is far from the initial random place we put this in. It's far from the centroid or what we would look at when we look at the class. We say, hey, this must be it, right? It's far from it. So this is all that was classified as red. That's all that was classified as blue, and this all that was classified as green. And so, okay, we compute the center. We compute a new center from what we have. And this is our new center for black. And you can understand why it's our new center, right? Because of course, if you see, no, not for red, because if you see how red is dispersed, you would expect the center to be, I think the last time I had something I could write with. Give me 1 second. Okay, I'll find it again. Oh, all right, don't worry. But basically, yeah. Well, what we're saying now is, so you expect the center to be closer to change, right? And so you recompute the centers. These are the new centers. You have, this is the 3 new black points. You try and assign again. You assign all the points based on their centroids, right? Which black is closest to it. Assign it, and then you compute the centers. And then you get to a point where at this point, it doesn't change anymore. So now you have 3 different classes based on k. K is equal to 3. And this is how we iteratively got there. I don't know if this answers your question. Or this makes it clearer.
Yeah.
Thanks. Guess I'm going to know that. A means you can do it in a few lines of code for people who are already thinking, how can I do this by code? You have scikit-learn, which contains k-means implementations. I've practically only did k-means by hand during my master's. I was 13. But I mean, you might want to do it by hand to try it out. I suggest that maybe once in in your career, you try to do it by hand. It's something I usually recommend. So it gives you muscle memory and an intuitive feel for the algorithm. And this is how you do it by using I mean, if you want to do it by hand, I'm not going to go into this, except you want me to read code for you. But basically, I think you can read the code and understand. Okay, so I went through this already. Right. So now, possibility of a local optima. I like minima because I think optima, but I know why they use optima here, because you don't know if it's a minima or a maxima. Some people say maxima, some people say minima. I think this just makes everybody happy. I think one of the things you learn as you go in the field is that machine learning scientists are always fighting over everything. Notation, how best to define something. Sometimes it just feels very trivial, some of the things we fight over, but yeah. So yeah, local optima. And so there's a chance that we can get like a less than ideal solution. One of the things that we saw over time is it now depends on where you start from, because you're starting from a random place, right? You're starting from a random place. And when you start from this random place, what happens is that it now depends on where you start from. So if you start from a randomization of k that is very close to your optimal solution, you get the optimal output. But you can start from a random place that you never really get the best convergence, or you never really get the best convergence. And this is the problem with k-means, right? The fact that it's not most times it's not reproducible. If you run it like this. So if I was reading something about a guy who wrote a paper, he did some experimentation. He got really great results, and then he sent his paper for publication, and everybody was happy with the results. And they said, oh, you should send this data so that they can reproduce the results. And the guy had been trying for 1 week and he was not able to reproduce that same result. And so you can get into that kind of problem with with k-means, where the results are not reproducible because it's actually depending on where your random starting point is. So what can we do? How can we make it better? Right? So, okay, this is an example of where we started from a bad initial point. Yeah, you have two blacks. The three of I'm sure you can see the three initial points, and then you keep going, and this is what you converge to, right? And this is bad. This is very bad. This is the kind of bad that makes spaceships crash, right? This is really bad. So what do we do? How do we change it? There have been many approaches to change it, right? Many approaches to change it, and a lot of people have come up with different algorithms. I think over the years I've read a lot. I can't remember, but I think the one that stuck most is what we call the k-means plus plus. When you say, which is you don't just do randomization anymore, right? You don't just do randomization anymore. You don't just randomize everything, right? And one of the things that I'm going to try to explain it to you. So basically, what you do is that you say, hey, I'm going to start, I need k, right? And let's assume here that k is equal to 3, right? And I'm going to randomly select my first centroid, center, whichever way. And so I pick my first centroid, I pick my first center, right? Now, I need to pick 2 and 3, right? I'm not just going to randomly pick them. What I'm going to do, right, according to k-means plus plus, is that I am going to sample, from my existing data points, right? I'm going to sample from my existing data points, and each of my data points are going to have a probability, which is the distance, which is directly proportional to the distance between my data point and the closest centroid. I know a lot of people are raising their arms. I don't know if I explained that very easily. But what it means is that, right? So I don't know if we know about sampling, right? You're not just picking it at random. You're going to now, if you choose your first center, right? If you choose your first center, it's going to be random. But your second center, what you're going to do is that you're going to take all of your data points, you're going to, because you only have one centroid now, you're going to look at what is the distance, what is the square distance between my data point and that centroid that I picked. Now you have all these distances, right? Now this distance corresponds to a probability. You're now going to change this into a probability. And each of your data points now are going to have these probabilities. That is the distance, because we have one centroid now, that is the distance between that data point and the existing centroid, right? And now you're going to sample from this. If you sample from this, what that means is that the points that are farthest from your current centroid have a higher probability of being chosen. Because of course the distance is larger, and then they have a higher probability of being chosen. And so what that happens is you're able, because if you look at this here, one of the problems here is because these two centroids started by being way too close to each other. And by being way too close to each other, we were never able to get out of that local minima. What do? We make sure that our centroids to begin with are as far from each other as possible. And so when we choose the first one randomly, the second one is going to be sampled, the probability, you're going to pick one of the data points as the center, as the centroid, and you're going to sample it based on the probability distribution, that a probability that is based on the square distance between the existing centroids. So you've picked number 2. Number 2 happened to be a center that you sample high probability, and based on high probability, you know that is as far as possible from center one. How do you pick center three, right? Now, center three, you're going to do the same thing, but instead of the probability just being to center one, your probability is going to be to the minimum distance. So the minimum distance between 1 and 2, right? Because you have 2 now. And the minimum distance is going to be the centroid. And what happens is, you know, in 3, you're going to have a center that caters for, that is far as possible from 1 and 2, right? And so what happens is, in the end, you're going to end up with these centers that are far enough as possible from each other, and in a sense, they're able to cater for all of the data points. So if you have K centers, you do this, right? If you have questions, you can ask before I move on, but I'm going to assume that you understand that. And so when we randomly initialize like this, it's no longer random. We have a better chance of convergence, right? What we see with the K-means plus plus is that we always converge better to a better, we always converge better, and we have much more consistent results. Cool. Anybody has questions? Zoom everyone is fine. Which is great. I was teaching a master's class one day, and this is where everybody lost their minds. So I'm happy that we're keeping it together. Okay. So I mean, this is basically just the algorithm for this. You know, you have a data set. Like I said, you sample your center, your first center, and for your second center to your K center, you sample based on X and the probability, where your probability is given by is directly proportional, I think, to the minimum distance between the minimum. There's supposed to, no, there's no summation. Oh, the minimum Ji, which is over the set of J's, which is the centroid mean versus the center versus the points, which is exactly the same thing I talked about, just a mathematical way to reference it. One question. Okay, I take it again. How is sentence chosen? Okay, cool. Like I said, you start from a random center, and from this, but just know there are two school of thoughts, right? The first school of thought is that you just pick any center at random within the space, right? But for this one, right, you pick a center that corresponds to a data point. So there are people who do random, there are people who do data points. It doesn't matter, you still convert whichever way. So what happens is you say, fine, I am not going to just initialize randomly from within the space. I am going to initialize randomly within my data set. So your first center is you randomly pick one of your data points, one of your input X, one of your input data points. You randomly pick it, and that is center 1. We good? Now you have center 2 to K. How do you do that, right? To pick center 2, you're also going to randomly select from your data points. So you're going to randomly select, and here let's talk about 3 points, right? Let's say we've already picked point 1, which we just randomly selected from one of our data points as our center. And we want to pick point 2. What we do is that we say, fine, we're going to randomly pick, but we're going to randomly pick based on a probability. I don't know if many of us have studied sampling before, but when you're sampling, right? Let's say, for instance, you have a coin. The coin, if you get heads or tail, right? You get heads or tail in this random scenario because why? It's an unbiased coin. It's 1.5, 1.5. I think it was Teddy that taught probability, so I'm sure that she taught you this. So but if you have a biased coin, I mean, I remember getting an interview question one time, which is basically if the probability of having a girl is 2/3 and the probability of having a boy by some means is 1/3, what's the probability of having 3 girls and 1 boy? And this was something I was supposed to figure out without writing anything. Basically, this is a bias situation, right? So here, the first one is random. Everybody has a chance to be picked. So you pick the first one. But in the second one, everyone has a chance to be picked given a probability, right? And we know that the ones that have the higher probability get a higher chance of being picked. So how do we give this probability? We say that, fine, for each of our X data points, the probability, we look at how many centers have we assigned before. For now, we're on number 2, so we've only assigned 1. So we say the probability is the distance between X and your center point, right? Your initial center. Now, some of the things that you put in your mind is, which is something that people, one of the reasons why people pick a random a point as the first center is because if you notice here, the point that you chose as your first point has a probability 0 of being chosen, 0, because the distance from itself is going to be 0. And so what happens is that you have points that are far from the current point that have the highest chance of being chosen. So you have something that is much more in math, I think we can say it covers the entire support of your data sets, right? Anyway, I think that's a mathematical terminology, if I'm not mistaken. So now you've done number 2, right? You picked randomly, but you picked based on the probability. So farthest points have a chance of being chosen. How do you do number 3? Number 3, the probability is going to be the minimum distance between 1 and 2. So you say, what is the minimum distance between 1 and 2? So you look at the distance between center 1 and center 2, and you pick the minimum, and that's the probability. And what that happens is, what that means is that in the end, data points that are both far from 1 and 2 have a higher chance of being chosen or being sampled. And somehow this gives you that full support k-means plus. And so you're able to have clusters that somehow cover your entire data set in a way that, you know, your initial centers are far enough from each other. And so you don't have local minimum convergence. Do you understand? Okay, I would assume, yes. Okay, now I'll start running. How do you select K? There's no right way to select K. Larger Ks usually have lower losses than smaller Ks, of course. I mean, because like I said, if we were to, if we said everybody should go to their own breakout room, then everybody would, you know, look alike. If we say, what is the center of your breakout room? It will be you. And so in that case, what you have is that you have a loss of 0. So if K is equal to number of data sets, right? You tend towards a loss of 0. And this is what this graph is showing us. So the higher the K, the lower your loss. Okay, good. So I decided to try this on real data and this data classification, 60,000 images. I know some of us have seen this, worked on it. Yeah, I mean the minimum between that particular data point and center 1 and 2. So you look at what's the distance between center 1 and what's the distance between center 2, and you take the minimum of that, and that is the probability. Sense? Some of us have worked with MNIST, and you know. So if we run a clustering based on k-means with k is equal to 50, which I'm trying to think of what this means right now. On 10 digits, right, we have, okay. Okay. So yeah, if you run this on k-means, you sort of get, in a way, recreating these data sets. You sort of get how, although I'm trying to visualize how this is. I think I'll come back to this. Can't really visualize right now. But yeah, one of the things is people say that we use k-means to discover the number of clusters. It's usually false, right? The thing is, it's very difficult to discover the number of clusters. It's very difficult to say this is the number of clusters that we have. And sometimes you have to do it by hand, and sometimes you have to do it by mind. And I think that's one of the reasons why semi-supervised learning is going on right now, because you can somehow simultaneously you can somehow simultaneously look at number of clusters, know the number of clusters, and to be able to learn from unlabeled data at the same time. Right. I have to run, looking at the time. Okay, principal component analysis. Any questions? Yeah, okay. No questions. Yeah, principal component analysis is one that I particularly enjoy, although it's very mathematical, right? It doesn't just find a way to cluster the data, it also finds a way to implicitly simplify the data, right, by transforming the data into a way that is easily understood. So what happens is, you are sort of saying that, hey, I have this data set and I have 9,000 points, right? How can I make sense of this particular data set implicitly by also removing the things that do not make sense for me, right? Or the things that I don't think are necessary for my clustering, but I still want to preserve the major axis of variation, right? Okay, so we assume that data is normalized. Can somebody just put what does it mean to normalize the data? Just on the chat. Okay, normalize, anyone? Somehow looks like remove the mean and divide by something. Anybody? Okay. So I'll leave that to us. What we usually do is sometimes called whitening, so you don't get confused. It's when we do data normalization. And what we want to do is that we want it to have zero mean and unique variance. And for this particular kind of unsupervised learning, it is saying that we want to find structure in our data, right? We want to find structure within the data. What is the structure in our data set? For instance, what is the principal point of variation? What is the principal dimension of variation? I mean, for instance, right, if I say we have all this data and then we have people within the breakout rooms, and you're saying that, okay, what is the principal mode by which I want to separate, right? I have all these data sets, but I have all these things, but I do not know how to separate. What is the principal mode, or what is the principal direction by which I want to separate? It's not usually straightforward, right? It's not usually straightforward because a lot of times we have all these data points. And that is why PCA has been used a lot in data compression, right? Because it reveals certain structure in data that then you can then say, fine, that it reveals certain structure in data, but then it minimizes the dimensionality of the data. And so this comes in an unsupervised setting that we usually refer to as, feature reduction, right? And so what is the loss saying? The loss is saying here that the new transformation of the data point, should be as close enough to the old transformation of the data, right? The new transformation of the data point should be as close enough to the old transformation of the data. For instance, there are many points you have in data sets. You have redundancy within the data. You have zero correlation within some data points, right? I don't know if we know what zero correlation means. And so how can we make sense? Right? Don't forget that a lot of things, machine learning comes back to making sense of the data, learning, understanding principal directions of variation. That's what machine learning is trying to do. All it's trying to do is understand the data better. And in a sense, how can we understand unlabeled data in a way that we know the principal points of variation? PCA to the rescue, right? And so here, we want to learn a compression. I'm going to keep this in our minds. I'm going to keep saying this word so that we get used to it. We want to learn a compression within the space, right? Where the compressed output is as close enough, the compressed output is as close enough to the input data point. Make sense? Have I successfully confused somebody? Okay, all right. So how do we do this? We will minimize over some data points, U and W, and we try to minimize the transformation of X using matrices U and W to X. Now, I think one of the reasons why this notation is very convenient is because X is always no longer in n-dimensional space, but it usually is now of k-dimensional space, right? So don't forget, and you sort of think about it, from PCA, we were mapping, sorry, in K-means, we're mapping all of these points to a centroid, right? We're mapping all of these points to a centroid, but in PCA, we are mapping each point to a better version of themselves, a lower version of themselves. And, you know, and if you think about it, when people say, I want to become a better version of myself, you know, they say, hey, I'm going to stop doing, I'm going to stop spending my time on social media. They remove and remove and remove. And so it's basically what we're trying to do. We're saying, hey, data point, I want to make a better version of yourself. What do we have to remove in a way that doesn't diminish the accuracy of whatever we're going to do afterwards? Dimensionality reduction. So one of the standard uses is to reduce the dimension of the input data. And so, yeah, the reduced dimension. So in a sense, the reduced dimension of X is X multiplied by two matrices, U and W, where WX is a reduced representation of X. So we have a transformation matrix, WX, which is a reduced representation of it. And then we have a rotational matrix that rotates WX back into the geometric position. So look at it. We start with X here. We have these data points. We have a principal set of variation. We have the principal angle of variation. We have multiple data points that, you know, make sure that, you know, they vary, right? But we don't seem to need this variance because in a way, if you plot a line through these points in hyperspace, you would see that you have a straight line. So all of these deviations contributing to extra dimensions might not be necessary. So what do? We multiply X by a matrix. And can somebody who is brave quickly tell me when you multiply a vector by a matrix, what does it do? So if you do, I'm sure some of us have studied the characteristic equation, maybe. So if you do that, what does it do? Anybody? Brave person? Yep, it returns a vector, but what does it do to the vector? It rotates the vector. It rotates and skips. So that is all matrix multiplication is doing. It's just rotating and scaling, right? And so when you think about it, it begins to simplify things. So here, we have a reduced representation, WX, which doesn't just remove extra dimensions, but it also rotates, X towards the direction where it is principally variant. Well, what that means is it rotates X into the direction where it is the differences in X is mostly visible. And then you have another rotational matrix U that rotates it back into our space. All right. PC optimization is not convex, as you will see a lot of it's very difficult to get convexity in unsupervised learning because you need you sort of I have a mental picture of you having to need labels to have a closed form solution. So if we use gradient descent, it's problematic. But we can solve it using what we call singular value decomposition, right? So what is single value decomposition? And I know that a lot of us might be lost here, but I'm going to try as much as possible to explain more and more, and also try to give us intuitions as to what's happening. So you compute the singular value decomposition of X, where U and V is orthogonal and X is a diagonal matrix. And then we return U for 1 is equal to K, right? S 1 to K, and W is equal to V, the transpose 1 to K, and then your loss is given by a summation over N, but looking at the diagonal matrix, right? Now, I'm going to explain this, so don't, okay. So one of the things I realized, the slide doesn't have a lot to, so I'm going to try to give you a mental picture of what's going on. Now, what we're trying to do is that we're going to say, we're looking for the direction of principal variance, right? We're saying we have this data point, but at what point does it vary the most? At what point does the differences happen to show up the most, right? At what point? And when you think about it, you conceptualize it like that, what you're saying is, hey, for instance, I want to ask a question like, if I'm going to be able to find the differences or the difference between I and Teju, for example, all right, I'm saying, can we focus on the point where both of us are maximally different, are maximally variant, right? What is that set of characteristics? What is that? Because I mean, you can talk about many things. There are endless features. But if you're trying to talk about the difference between I and Teju, for instance, you have to calm down and settle on a set of features. And when you're settling on the set of features, you want to settle on the features that optimally describe how different we are. And if that is what you want to do, the question is, how do you do this? Right? How do you do this? So you calculate what we call a singular value decomposition. And I'm going to give you like a general overview of singular value decomposition. And what that is, in a sense, is this, right? I'll just give you a general overview so that you don't get lost within the mathematics of singular value decomposition. I'm sure when you when you check the page on Wikipedia, it's a bit complex with all the maths. But what you're trying to do here is that if it just feels like if you're trying to find differences, what do you have to do? You have to first of all say, how does every feature, how do they change with each other? What is the difference between them? How do they correlate, right? And so the first thing you do is that you calculate what we call a covariance matrix. When you calculate a covariance matrix, right, what happens in a sense is that from this covariance matrix, if you think correctly, if you know correctly, the diagonal of your covariance matrix is going to be your different variances. So it's going to be saying, how is it, how does each feature differ with itself? But that's not what you're looking at, right? What is basically much more important to you is how two different features, how two given features differ with each other, right? And so now what you now do after you've done that, you have this matrix of covariances. And you know that if you have n columns for the covariance matrix, can somebody quickly tell me what your covariance matrix will look like? It will be n times n, right? sorry, I already said it. It'll be n times n because you're looking at how each column, correlates to another column and to itself. What is the, how are they similar? Do they look each other? And don't forget, you're looking for the subset of features that encapsulate the greatest difference, right? So now we're down to covariance matrix. Good. Where do we go from here? We say, fine, I have a covariance matrix that tells me how these features look like or how they change. Let's say you have a covariance matrix that, let's say in the hair dimension, I have long hair. Sergio has long hair. Like, okay, there's not so much variance, right? So we're saying, okay, fine. How does skin color change with hair? How does hair change with, fingertips? A lot of these features. And then you sort of see, what are the features, what are the subset of features with the greatest covariances that, best describes, or most distinct covariances that best describes what's happening with my data. So you have this particular matrix. Now, the matrix is always very complex. So now you're saying, hey, within this matrix, I want to find the direction where the most, I don't want to say variance, but the most change is happening. So at what point in hyperspace do they vary the most? And then you have another tool to help you do that, right? Eigenvectors and eigenvalues. So the eigenvectors will tell you the directions in which you have the most in which you have the most variance. So it projects your data into hyperspace. I'm trying not to be very mathematical. And then it finds the principal directions. It's the word, the phrase, the principal direction. So it says, okay, fine. After I've calculated these covariances, I projected it into hyperspace. I see that these are the principal directions. Oh, hair is varying a lot with, skin color, or I can see that, when people have, the same hair, they always have different skin color. Or when I see that when people have, when people like rice, they always like spaghetti. And so we probably do not need like spaghetti or like rice within our data set. So you're saying, hey, I'm finding the directions of principal variance or principal directions within my data set. And that is where the most is happening. And we have the tool eigenvectors and eigenvalues. If you didn't know what they were used for today, and so the eigenvectors are the principal directions, and that is why they are vectors, right? They're saying, hey, the most change is happening here, here, and here. And the eigenvalues are telling you the amount of change that is happening. Do you understand this? And so the biggest eigenvalue would be the one that is having the largest thing, and they're always orthogonal to each other. So in a sense, you're always assured that there is a 90-degree angle between, and that is why it's telling you that U and V here is orthogonal and S is a diagonal matrix, right? And so basically, what now happens here is for principal component analysis, U is always equal to V. So forget singular value decomposition, just think about it that you have U is equal to V. And, right, what happens is that your diagonal matrix is your eigenvalues showing you the direction or how much is happening within this direction, right? Right? Does it make sense? I hope nobody's lost because I don't know how to find you. Okay, I will assume that nobody's lost. So now that we know how this is, right? So now that we say fine, we have our eigenvectors, and then we're going to return these vectors that somehow tell us about the principal direction, right? And let's say you have n by n. So in this n by n, you're going to have n eigenvectors. One, don't forget that this is symmetric. Now, to find this, so that you know that you have a closed form solution, don't forget that our x value is, no, let's see, our covariance is symmetric. Our covariance matrix is symmetric. And I know that some people know why, some people don't, because the covariance between column A and B is equal to the covariance between column B and A. So you're always going to have a symmetric matrix, and that makes it very easy to do a singular value decomposition. But I'm just going to give you the intuitive feel of what's happening. So you have U is equal to V because it's principal component analysis. If you want to study singular value decomposition, which is used in many other areas where U is not equal to V, you can try that. Since U is equal to V, now what is your loss? Your loss, and U is equal to V, and V is a set of eigenvectors that define the principal direction. Now, what do you want to do? You want to take the first k principal directions. So you're taking the first k directions where the most is happening. Do you understand? First k directions where the most is happening, and then you're leaving the rest. Now, what is your loss? Your loss here, and don't forget that I said S is a diagonal matrix that contains the eigenvalues, and the eigenvalues is telling us the amount of change that is happening in each eigen or vector direction, in each principal direction that is now the composition of your V matrix. And so what we want to do is that we want to minimize as a loss. Now you have to be super attentive here. We have to want to minimize the summation of the squared eigenvalues from k plus 1 to n. Now, what that is saying is, and I think that it might be, now this is a loss, but it might be a bit complex to think about it, because in a way, what we're trying to do is we're trying to say that, hey, after I have taken my k principal directions, I have n principal directions in terms of the eigenvalues. I'm just going to take k because I know the rest, not much is happening. I know that I've already sorted them by what is happening most to what is happening least. And so I'm just going to take the first k principal vectors or principal directions. And now what I'm saying is that the eigenvalues, which amounts to the to the variance within this remaining principal directions that I am discarding, should be minimized. So my loss is computed as what is the eigenvalue of all of these remaining directions that I am discarding. Okay. Oof. Okay. I think we got there. Yeah, and so this is how you come. And then when you think about it intuitively, what you're saying is, hey, but if I'm minimizing this, what this means is that, I mean, if I'm going to minimize this loss, in the end, I'm just going to take everything, right? Because at that point, I'm assured that my loss is equal to 0. But then you have constraints of k, right? You always have this k constraints. And if you go back to k-means, like I said, the optimal k, even in k-means, is that everybody had their own breakout room. But, I mean, when life gives you lemons, you make lemonade, right? So we can always have as many Ks as we want. And so we have to define this by this, right? Okay. PC is a few lines of code in Python. If you want to do it yourself, get an intuitive feel for what SVD does. And that's because we already have something that does SVD. So I already told you how to compute your singular value decomposition. You first of all do the covariance. From the covariance, you find the eigenvectors and eigenvalues of the covariance matrix. And if your covariance matrix, which in this case is our covariance matrix, is symmetric, then what you have is that U is equal to V, and in this case, your loss is just the sum of, the remaining case that you are not taking. And then now what you return is a transformation of your original data point towards the directions towards your principal direction. So you take the principal directions that you want to keep, and then you multiply that. Okay, I have a lot of. Oh wow, people are lost. Okay. I don't know if we.
I just want to say, guys, this is one of the most intuitive explanation you would get. So I definitely encourage that you rewatch the video, Google, and come back to it. But it's pretty nice. Thanks, Olumide.
Okay. All right. I mean, I would also try, if I think of maybe a much better intuition, what better way by which you get a better intuition of it. I would try to do that. I For now, I feel like Teja said, I'm trying as much as possible not to dwell on the maths, but to just give you insights as to what is going on. I feel like you can always get the maths, when you understand what they're doing and what it's doing. Okay. Oh, and so like I said, when you multiply, and then you do a transformation of your x into the direction into your principal directions by multiplying your U matrix or your V matrix, which is the same, transposed to K with it. All right. Sorry for people who are lost. Okay. So how do we now do dimensionality reduction, right? How do we do it? So we have this is your original data sets, right? So if we take, let's say each number, right, and the MNIST data set, and we take the first, the 50 principal components. So we're saying we're taking each number, right? We're forming a covariance matrix on each number, and let's say the number is 256 by 256, and then in principle, this is how you do it. 256 by 256 means that if you, most people usually, I would do it, I would put it in a vector. So you have 256 times 256 columns, right? And then you have, you do the covariance matrix of that, which is 256 times 256 times 256 times 256, four times, the covariance. And then from there, you can choose, the first 50 principal components, which is pretty small when you think about the number that I just called, right? When you think about the number that I just called, it's pretty small. And so when you take the first 50 directions, this is what you get. It's not as clear as what we had before. Let me see, where did we have this? It's not as clear as this, but you can already start to see the outline. So these are the first 50 principal components for the MNIST. Right, and these are the original images. So these are the principal components. And when you use these principal components to transform the original data, you have this, which it's pretty clear. So having to go from a dimensionality, I think it's 256 by 256, I can't remember what the MNIST number is, to 50 means you can do a lot more things and still conserve the clarity within your data set. This is K is equal to 2. This is when you take only 2, the 2 principal directions. This is when you take 10, when you take 100. Right. And so basically, this is not, this is the original image. Sorry, this is the original image. Yeah, I was wondering that. And this is what you get when you have 2. This is what we get when you have 10 principal components. This is what you get when you have 100 principal components. And in reality, this is already clear. And if you're going from, and I think the original, if you had the, what is 256 by 256? I can't remember. But if you're going from that number to 100 and you're already having this clarity, it might be a good trade-off depending on what task you want to do. But then instead of reveals a structure within the data, you'll forget you're revealing structure within the data. Okay. They're useful as unsupervised algorithms, but they're often used for data preparation, right? Often. Dimensionality reduction with PCA, you run the PCA, you get a W matrix that is K, you transform the inputs, like I said, from x to xi, which you've now reduced the number of printable components, and in essence, you've reduced the number of columns. And don't forget, anytime you see a matrix multiplying a vector, you know that the matrix is carrying out a particular operation on the vector. Always have this at the back of your mind. These operations can be, not limited, no, I think limited to rotation, reflection, scaling, right? And so when you have this matrix W, it has the ability to scale, to reflect, and to rotate. And so you're sort of changing your data in a way that reveals maximum variance and discards the rest, right? Radial basis functions, right? And so this is something where, you were talking about the circle where you're trying to have radial basis functions, try to, I'm not going to go in depth into radial basis function. I don't even think I have the time, but principal component analysis, K-means is used to extract the centers. Like you can say, oh, I have this initial centers, this initial means, and then you can feed that into your radial basis functions or your radial basis functions to help you in doing whatever you want to do. Or create new features, basically using radial basis functions. All right. Oh, last slide. So I am open to questions, concerns, problems. Anybody?
Thank you so much, Olumide. Any questions?
Anybody wants to go over what they're lost over? Maybe I can help clarify anytime.
Jerry, do you want to go?
No. The thing is, I think it's more of the terms you was using. So I need to first understand those terms. So I have to go back and watch the video. So it's really having the class. So don't worry about it.
Is there any term that you want me to explain? Any term that I can just help you with? Off the top of my head now.
When you start mixing covariance, principal, something, again, so I need to go and check what each of those things mean.
Okay. So what's the covariance?
And then come back to the video.
Yeah. You know what a standard deviation is?
I kind of, yeah.
Okay. You know what variance is? You know what variance?
Yes.
Exactly. Okay, so you already have all the tools to understand covariance. So when you do variance, right, when you're trying to find the variance within a particular, so let's say, I think we call it first moment, second moment. First moment is mean, second moment is standard deviation, I think. But what are you trying to do with mean? What is the story you're trying to tell? Because this is a question I always ask myself. Everything I'm doing, whether mathematical, has to be able to tell a story. So when I'm calculating the mean, right, I'm trying to calculate what is the central point. I'm trying to ask myself, if I could take all of this data, throw it away, and only keep one, what is the one data point that sort of sits in the center that tells me a lot about my data? And so you sort of say, hey, I want to calculate a mean, and then we do mean, and now average, mean, whatever we want to call it, has become normal. We're always doing it, right? Because we don't have the bandwidth to keep everything in our minds. If somebody offends you 5 times and is good to you maybe 2 times, we keep the average and we say, oh, this person is a bad person, right? The average tends to be bad. Now, but then over time, we realized that, okay, yeah, we need to be able to tell another story about our data, which is, yes, we have this mean, but we know that, for instance, -1, 1, and 0, they have a mean of, what's the mean? They have a mean of 0, I think, right?
Yeah.
-0.1, 0, and 0.1 also has a mean of 0. So we now started asking questions like, how can we talk about how far off are the original data points? How far off from the mean are they? And so we came up with this thing called variance that tells us a story about how far off, so how far off they are from the mean, which in essence, it's trying to ask another question, which is how is the numbers, how are they changing with respect to each other? Do you get? And so we have a value in the end called standard deviation variance or whatever we want to call it. That's sort of, so we have a mean that tells us the middle, but we have a standard deviation that tells us, hey, these guys are far off. So this one is -1, you know, that kind of thing. And then you have this one, they're much, much, much close to the mean. And so we can treat them differently. But now, in a sense, you're looking at how this thing is changing within itself. But then you might want to ask another question, which is, hey, I don't just want to know how it's changing within itself. I want to know how it's changing with respect to another feature that is changing, right? So let's say, yes, I want to know how, for instance, how my eating habits, right, is changing with respect to the data on how, or the column on the availability of food. You know, that's a very interesting thing to know. Do I eat more when there's food? Let's say you want to lose weight, and then you're trying to analyze the data, and you realize that once you have the amount of soda drinks you drink is directly proportional to how much soda you have in your fridge, right? And say, hey, you track the data. But now, how do you say that story and say, hey, the more soda I have in my fridge, the more I drink soda, or the more food is available in the house, the more I eat. So in that, the story is going to be say, oh, I can calculate this using what we call a covariance, right? A covariance now measures how do they change with each other. If you have 0, it means that they are completely decorrelated. They don't affect each other in any way. If you have 1, it means that with the more soda you have, in a sense, the more soda you drink. The more food you have, the more food you eat. If you have -1, it means that the more soda you have, the less soda you drink. And the more food you have, the less food you drink. The less food you eat. And most times the value stays between -1 and 1, and it tells you this particular story that you want to know.
Well, isn't that correlation?
In a sense, there is a difference. I can't say the difference off the top of my head, but there is.
I think it's once you now standardize it, that's when it's become correlation.
Variant. Okay. When you standardize it, it becomes correlation. Okay.
Yeah.
Great. Thank you. So basically, that's the story you're trying to tell. But now, what we're now trying to tell is, okay, fine. I have all these columns that correspond to data for something, eating habits, cooking habits, whatever they are. And to tell me a lot about what is changing, how they're changing with respect to each other, I have to first of all calculate what we call the covariance, which now tells me that story about, okay, this column is changing in this direction, you know, with that other column and changing in this direction, with that other column and changing in that direction, with that other column. And so you have these columns that are changing with respect to each other, whether increasing, as one increases, the other is decreasing, or as the other is increasing, the other is decreasing, or they're both decreasing in a sense, or some that are uncorrelated. And then you have this matrix that tells you this story. And then you now say, okay, fine, I have this matrix. I have another story I need to tell. I have another question I need to ask. So with all these changes, with all these variations, covariations that are going on with this matrix, what is the principal direction within this matrix where I have the most variation, where the most variation is happening? Let's say the most variation is happening within the combination of cooking habits, soda habits, and eating habits. Yeah, maybe that is where my first principal direction might be. So now you're saying, hey, I want to know that, right? And you're saying, fine, I have the tools. Mathematics are just the tools to help you tell your story. And so I'm asking this question, I need an answer. How do you use it? I have the covariance matrix, but then I can find these principal directions using, you know, an eigenvalue decomposition of this. And so my eigenvectors, which are vectors in hyperspace, are telling me hey, these are the principal directions within your data. Exactly. Thank you for the correlation. Yeah. So these are the principal directions within your data, right? And since you have a covariance data, it's telling you the principal directions within your covariance data, which is telling you the principal variation, which are the principal directions of variation. So you're saying, okay, fine. Now I have these directions. I'm just going to keep the first K where I'm have the most stuff happening. And I'm going to kick out the rest. I mean, right now I'm planning for next year, and there's some things I'm going to drop, and there's some things I'm going to focus on. And I'm looking, okay, what's the principal direction of variation? What are the things that I'm going to drop? When you do your New Year plan and you're saying, hey, this is my New Year resolution, I want to focus on this, you're essentially setting your principal directions that will give you the maximum output, right? And in a sense, that's what we're doing here. We're saying, okay, now that we can calculate the principal directions that give us the most of our data, we can just take a couple of it and leave the rest, and we are not bogged down by all those details. And then we can now focus. I hope it's
Thank you very much. Got
understandable. Okay, great.
Well, left to me, I don't want this class to end. Just like the sound of your explanation. So, any more questions? So we can keep Olumide on the call for a few more minutes.
Any more? Can ask your questions. If I don't know, I'll tell you. I'll get back to you.
It's not the end of life.
And trust me, I don't know everything. I know that I don't know the facts.
That's when you know you're on another level of boss. It's like you can
Yeah.
I'm going to look it up later, but I don't know it right now.
Yeah, I'll tell you. I'll send it to you.
Any more questions, guys? Now is the time to clarify. Maybe there's something he said that you didn't get. You were thinking to yourself, oh, I'll just look it up later. You can just ask now.
Ask.
Okay, on this slide, you showed a way that with the K-means and PCA, yeah, there's a correlation between unsupervised and supervised learning of sorts. I don't know. I'm talking about the first two lines on this slide.
Okay. Okay, the first two lines, although useful in their own right, yeah, it's okay. So it's used in data preparation for supervised learning, right? That's what it's trying to say. So for instance, and so I mean, visualize this. Let's say you have labeled data. And that was what happened to me in 2013 when I entered this competition. I had labeled data. I didn't have GPUs. I didn't have, I didn't have the kind of compute that we have now. And so this labeled data, the columns was a lot. I could not load that and train on that. So I needed to reduce the dimensions of my data points so that I could be able to do a training with the kind of limited compute that I have. And sometimes not just limited compute, other times it's just basically, you want to simplify your data as possible. And so what you can do in this case is that you will take a PCA of your data, right? And so you find the principal directions, you reduce it to the principal directions. And when you do, right, you have a much more simplified data. And basically this is how PC, and then you can now run a supervised learning algorithm with this reduced X. So this is how you can use that. And this is really mostly how it's been used. Radial basis functions with K-mean. So radial basis function features are in a way trying to define for a set of classes features. So you're saying, okay, fine, I have features. Let's say you have images, right? And then for a set of images, you want to define a set of what we call radial basis features, right? For your images, and which is much more it's a different topic where they sort of correspond in sort of a radial way. I don't want to get into it, but basically now you want to use these features, right? You can first of all define case centers. And then, now after you've extracted these case centers, right, you can now define radial basis features around each of your case centers, or now transform from basically this feature sets that you have that is very large to a k-dimensional feature set that is represented using the radial basis features. And I think this is somewhat used in super vector machines, especially when you're trying to do the kernel trick, which is a supervised learning algorithm. Right?
When you started this class, you showed us the hypothesis function for unsupervised learning, where we did not have Y, but for supervised learning, we have Y. So are you saying this PC is giving us a Y we can work with?
You can hypothetically say PCA isn't giving you a Y. You can hypothetically say that K-means is giving you a Y. Well, your Y is somehow biased. Your Y is dependent on the number of centers that you put. I mean, one of the things that you can do is, let's say you know that your data set, you have pictures that contains only dogs and horses, right? And you're saying, I don't want to manually label each one, so I'm just going to run k-means on it with 2 centers. Yeah, that's the way you can do it, right? And then you get your Ys. But physical component analysis is much more in the sense of dimensionality reduction. So it's mapping you to a different subspace, that is a reduced dimension of your original subspace, of your original space. Cool. Are we happy?
Is everyone happy? It's really important that you're happy you're on this call. that makes a difference. So are you satisfied for today? Okay.
You're not satisfied, but you're going to let me go. Okay. All right.
Okay. Well, thank you so much, Olumide. It's a pleasure to have you here. We're very fortunate, and really appreciate you taking the time to take 2 classes, and looking forward to bringing you back for future iteration of many other things we have in store. And that's a wrap for week 15, everyone. We won't be having tutorials today, and the last tutorial would be next week. The last class would be next week for the cohort. The last tutorial will also be next week. So looking forward to that. And also thank you to all of the team that have submitted their project proposal. We'll get back to you tomorrow. Oh my goodness, I almost forgot attendance. I'm going to send it in